So excited. So, okay. So, yeah. So we've got dx sine x dx, and if I want to take that derivative, right, I can write down that product rule. That shows me you know you need a product rule, and you know the product rule of what, right? Now here, I mean, in the end, I don't care if you look that up. That's fine. I mean, so, you know, the next thing would be a 1 times sine x anyway. Heck, how do I know if you looked that up or not? Right? I don't know. You know, so, and then the same thing over here, plus x cosine x. How do I know if you looked up x, you know, the derivative of sine x, or you had it memorized? I don't really care. Okay, so you showed me here, you know the product rule, and somehow or other, you know the derivative of x and you know the derivative of sine x. So, you know, you're showing me that you're doing some calculus type things. So, so that's the idea in those videos. I have 3 of them. I think the 3 of them are sufficient. Certainly, you know, if you have any questions whatsoever about whether you're doing enough, just shoot me an email, you know, ask. You know, and just kind of think about some things like this. You know, if I didn't need this, well, in a lot of ways, I don't know that I'd really need to give you an exam. Because when all is said and done, I don't want to give you a typing exam, right? You know, and pretty much, if you just need to type that into something like, you know, I've used in here Desmos and Sage Math Cell, and but you know, there are other things out there. I mean, you can, Wolfram Alpha. I don't know. There's probably some Calc Help thing somewhere. You know, but you just type it into Google, it'll give you an answer. I mean, you know. So on the one hand, you know, I don't want to ignore that and pretend we're not in the 21st century. And so it's that balance of trying to allow the 2 things. Okay, so you can obviously check your work. Not a bad idea, you know, and don't start too late on the whole thing, and you'll have plenty of time to check your work. Okay, but again, if you have any questions, contact me. Do not talk to anybody else about it. That's the one place where you do start having big problems. You know, if you collaborate with someone else, whether they're in the class or out of the class, on something like an exam, actually, amazingly enough, I think we tend to find out about it pretty readily. And, you know, I can't say that, you know, I've always known if somebody, you know, whether they were in class or out of class or something like that. But on the whole, I would say, you know, faculty do a reasonable job of noticing such things when it happens. Honestly, sometimes they don't care because the person failed anyway, you know, kind of thing. And so it's not worth the hassle from that standpoint. But yeah, so don't do that. You know, mostly I find people break rules when they panic. So if you don't put it off and you are willing to contact me, you probably won't panic. And so that's a good thing. And okay, so with that, I don't really have any more to say about it, I don't think. Anybody have questions over anything at all? You know, I mean, the exam, homework problems, anything that you have you'd like answered?
I have a question.
Yes, sir.
I actually have two questions. Question 31 and 41 of section 3.3.
Okay, so 31 and 41. So in 31, we are asking to find the critical numbers, find the open intervals where it's increasing, decreasing, and apply the first derivative test. Use a graphing calculator to confirm your results. Okay, so in 31, oh yeah, we got an absolute value, and so yeah, that is, you know, a nice thing. There's a great test question right there. Okay, absolute value. I don't think I have I don't think I have an absolute value on there, but great test question. So f of x is 5 minus the absolute value of x minus 5, I think. X minus 5? Yeah. When I go to take the derivative, this is where you have to be careful, because this is actually a piecewise defined function. Okay, so what this function really is it's 5 minus the quantity x minus 5 whenever x is at least 5. Okay, because it's the positive number, and so there's a minus, and minus a positive number is minus a positive number. But if x is less than 5, then the absolute value is actually the negative of that thing. Okay, so it's the negative of x minus 5, but I've got minus a minus, and so I could write it as 5 plus x minus 5. So I have two different pieces to deal with on this function. Now, so this is a nice function. This is a nice function. Linear, I mean, you know, I'm not going to have any critical numbers, well, because I know it's linear. I'm not going to have any critical numbers out here where x is bigger than 5, because it's nice. And it's a straight line. Okay. Now, I can take the derivative and so forth to make sure, but, and the same thing here. The only place I think I'm going to have a problem is at 5, because that's where it changes. Now, if I take the derivative, f prime of x, well, that would also be a piecewise defined function. And so, you know, just looking at it here, I would get -1 when x is greater than or equal to 5. And then down here, just +1 when x is less than 5. Okay, because the constants disappear. And so we see that, yeah, you know, the derivative is fine. It's never 0 anywhere. But it is undefined at 5. Okay, it's undefined at 5 because the limit as I come in toward 5 from the right is -1. The limit of this thing as I come in from the left is going to be 1. Well, limits don't match. The limit's undefined, therefore the derivative is undefined. And so our critical number, so that was part A, I think, critical number is 5, x equal 5. I'm trying not to kick my cord here, that's why I'm leaning out. Just want to show you my dexterity or something, I don't know. But so our critical number is 5, that's the only one. Now, on the open interval from 5 to infinity, Well, it's not really hard to figure out what the sign of the derivative is because it's a constant -1. So the part B, as I look at my open intervals, I have the interval from 5 to infinity, and I have the interval from minus infinity up to 5. And, here it's decreasing. And here it's increasing, because I have my negative and my positive. So that part was simple. I didn't have to plug anything in because it's just the constants. Otherwise, I could try 4 and 6, right? I could put in 6, evaluate whatever was here, see what I get. Put in 4, evaluate whatever's there, see what I get. But in this case, I had the negative and the positive 1. And so we have that. Well, so if it's on the left increasing, right? So it's on the left, it's increasing and then decreasing. Looks a lot like a maximum to me. Okay, and so we have a relative it's a relative maximum. Actually, in this case, it's also an absolute maximum because there's nothing else, nothing else that's going to be bigger. And at 5, what do we get? 5? Yeah. So I don't remember how this is worded. What did it say? Find the open intervals, apply the first derivative test to identify all relative extrema. So we did that. So we identified it as a maximum. Technically, I don't know that the way they asked the directions, I actually need to define what the y value was or is. It doesn't hurt, right? So at x equals 5, we get 5, and so our point here is at 5, 5. And then I can always go to Desmos and type that in and should get that picture. Okay. Any more questions on that one? Nick, anything else on that one?
No, you answered my question.
Okay, great. And then the other was 41?
Yes, sir.
Okay. And in 41, we're only looking on the interval 0 to 2 pi, but it is an open interval. Okay, open interval. So we don't get to, it's always easier on a closed interval because on the, a nice continuous function on a closed interval, all we have to do is find those critical numbers and evaluate. We don't need a first derivative test or anything. We can just evaluate everything and evaluate it at the endpoints. Okay, but as soon as it's on an open interval, the problem is it may run off to infinity or negative infinity or something like that. And so, or it may, I guess, be bounded, but there's no maximum because if it's an open interval, it just keeps going. Okay, so, but it may be bounded. So, an example of, something that's bounded on an open interval might be that, they say 0 to 2 pi, and they mention a cosine function there. So if I just do this, like that, from 0 to 2 pi of the cosine, but I put open intervals here, or, open parts here, you see there will be no maximum. Okay, even though I know it goes to 1 right there and goes to 1 right there, it never reaches it, so there is no maximum. And, okay, so, let's look at this. I can probably end up filling that in. Oh, no, it's x over 2 plus cosine of x. So let me just get rid of that. So in 41, we have some function that is x over 2 plus cosine of x. And now again, this is just on the interval 0 to 2 pi. And so if I want to take that derivative, because again, part A was just, well, it wants to find the intervals where it's increasing and decreasing. Well, I probably need to find the critical numbers to help me do that. And so f prime of x is 1/2 plus a negative sine of x. And to find the critical numbers, I'll set that equal to 0. I'll also try to figure out whether it's undefined, but again, very nice function, a constant, it's defined everywhere. If I move the sign over to the other side, but that would just make me sad, so I'll also switch sides with the two things. Sine of x equals 1/2. And now, if you have something like this, again, it sort of grieves my heart that probably too many of you, don't just look at that and go, oh yeah, that's a whatever kind of triangle. At least that's my guess. Because yeah, this is, when I see a 1/2, I know that's a 30, 60, 90 triangle, or pi over 6, pi over 3, and pi over 2 right triangle. But you can always go to Desmos or something and say, what's the arc sine of 1/2? And now, again, though, you have to be careful because we're on the interval from 0 to 2 pi. The arc sine returns answers between what and what? Good question. Yeah, between minus pi over 2 and pi over 2, or minus 90 and 90. And so it doesn't necessarily jive with the interval we're using here. Now, when I do this, though, yes, for sine x equal 1/2, I should get x equals pi over 6. And at the risk of forgetting to come back to the board, let me jump down here and let's look at Desmos. Do I have Desmos up? No. Well, actually, get up very fast this way. Okay, so, well, I thought I could get up there very fast. So, if I just type in sine x equals 1/2, so these are all the spots that's true, and no, okay, so I thought maybe it would give me a beautiful answer that way. Okay, so here's another way to sort of trick it into possibly giving you a great answer. There's sine of x. Here's, I don't know why that's still there. That's from the back here. It's kind of weird. Let me click up there. Can I not get rid of it? Let's click out here. There we go. Okay. See it? Oh, beautiful. Okay. So y equals 1/2. Oh, okay. And now, look at that. Desmos actually tells me it's pi over 6. So, with nice ones like this, I'm pointing at the board, Nick, sorry. So, with nice ones like this thing, pi over 6, it tends to give you really nice answers. Square root of 2, not so much, but if it's trig stuff with like pi over 2 or pi over 4, and there's 5 pi over 6, and that is inside 2 pi, I can come out here, and so, I have 2 answers inside of 2 pi. Here is the last one, but it's 13 pi over 6, and so a little more than 2 pi. So I only have the 2 answers, pi over 6 and 5 pi over 6. And so, come back here. And so I knew one answer right off was pi over 6. If I worked with the unit circle and all that, I could get the 5 pi over 6. But Desmos will do that. And again, that's fine. Okay, I'm not teaching an algebra class. I'm teaching a calculus class. And so x equals pi over 6 or 5 pi over 6. And now, just because we are talking about the exam today and so forth, from Desmos, right? Because if I just see that, I don't know, I realize technology is out there, but if you screw it up, I'd like to have an idea of why. And, because if it's right, actually, no problem. But again, if everybody just has the answers, then I kind of ask, well, okay, which one of you did the exam and then gave it to everybody else, right? So it's just the more you write, the more I can tell what you are thinking, and that's what we want to know. So, okay, so we got those for our critical numbers. So that means our intervals are from 0 to pi over 6, from pi over 6 to 5 pi over 6, and from 5 pi over 6 to 2 pi. And the derivative should be the same sign in all of those. And so I can check its sign by plugging it in here, 1/2 plus or minus 1/2 minus sine of x. But how would I probably do that? I'd probably do it with a calculator. Well, hey, Desmos is a calculator. And so I would just come back here again. And, well, to make my life easier, I might do something like f of x equals the original function. So, what was it, x over 2? And then plus cosine of x, like that. So there's the original function, and there's the pi over 6, so it was increasing until there, then decreasing, and then increasing. So, well, I could come out a little bit. But, just to look at my intervals better, actually, I could do f prime of x. And now it's getting kind of hard to see things, so I can come over here and turn stuff off. I might want to turn off the f of x function, but here I can see my f prime of x, and I see it's positive over here, negative in here, and then positive all the way out to here. And but I could also do things like, well, pi over 12 is between 0 and pi over 6, so I type in pi over 12, and I get a positive number. Okay, and then pi over 2 is between, let's see, f prime of pi over 2, so pi over 2, that's between my pi over 6 and 5 pi over 6, because it'd be 3 pi over 6. And then finally, I could go out here to f prime of pi, maybe, and I get 1/2. And so, you know, for each of these intervals, what did I have? I had negative and then positive and then no, I had positive and then negative. So this was increasing, this one was decreasing, that one was increasing. And let me go back where I have the board here. So I just put those arrows up right there. And so we have our increasing, decreasing, and increasing portions. And then, yeah, apply the first derivative test and confirm your answer. So first derivative test says, well, I was, you know, as I go across these intervals, okay, I was going up, then I was going down, then I was going up again. And there you go. There's a relative maximum, there's a relative minimum. And again, the text in this particular case didn't seem to ask for the y values. Maybe, I don't know. First, well, to identify, I guess when they say identify, to identify an extrema, I guess I would need to give you the x and y values. Okay, so if they say identify, yeah, you should probably give the x and y values. Okay, any more questions on that one or anything else? No? All right. Well, then what I'm going to do is talk a bit about the second derivative and probably look at a little drawing of stuff too. So this is just starting 3.4. In 3.4, we learn that actually the second derivative of a function can help us out in understanding the relative extrema, just the general shape of the curve and what's going on. And so all right, so 3.4, we're really looking at the second derivative. And of course, the second derivative is this is just the rate of change of the first derivative. It's the derivative of the derivative. Okay, so two basic shapes when we think about the second derivative. We have a shape like that, any part of it. So for instance, you know, I could have just drawn that much or that much or that much or something like that, but any part of that shape. And probably if you were to talk about it being cupped, you would say cupped down. Okay, and this shape in calculus books, they call it concave down. I wish they'd just call it concave, but they don't. They call it concave down. And then the opposite, from a function point of view, is something like this that's cupped up, and they call this concave up. And I wish they'd just call that convex, because that's what we would call it usually after a calculus class. It's kind of funny how, you know, I'm guessing that maybe engineers or something use this. I'm not sure, but for whatever reason in calculus classes, we go with concave down, concave up. Maybe we use it because, you know, it rhymes nicely, you know, frown, concave down, ha, I don't know, easier to remember, or cupped up, concave up, you know, cupped down, concave down. Not sure, but that's what we call those shapes. And, you know, in any part of them, so again, if I take any little part of those curves, I would still call them either concave up or concave down, depending on which one they came from. Now, in those shapes, when you look at them, if you start drawing tangent lines, you know, there are tangent lines on this thing. What we notice about the slopes of those tangent lines is, in terms of real number values on the number line, right? This is the biggest over here, right? I don't know what that slope is. You know, maybe that's a slope of 7 or something. But that is not as big. And that's definitely not as big because it's negative. Right? So here's the biggest, and as we go around here, we get to the smallest. Okay, so what we see is on the function, the rate of change of the function is decreasing. Okay, and that's where you got to be really careful about words. Because see here, the function's not decreasing, but its rate of change of the function as I move along is decreasing. The derivative is bigger here and smaller there, so its derivative is decreasing. And the derivative is its rate of change. Okay, so here it's decreasing, and here the rate of change, you know, so there are tangent lines. Okay, this would be the smallest, and this would be the biggest. Okay, so then you get all these matchings of the words increasing and decreasing. Okay, so let me redraw them here. So if I have this concave down thing and I split it here, what we see here is that the function's increasing, but it's increasing less and less and less and less and less. So what we can say is, oh, over here, we could say the function is increasing at a decreasing rate. So that you might hear. So it ends up mixing those words. But it's the function is increasing. Yep, it is. But it's increasing at a decreasing rate. It's decelerating. Okay? It's not growing as fast as we move along on the x-axis. And then here, I'm not going to write the function is part here, but here we're definitely decreasing. But the way they would talk about this, they would say, well, it's decreasing, but it's decreasing faster and faster and faster and faster. So they would say decreasing at an increasing rate. So it's, here we're just trying to get our English to match the picture and so forth. So if somebody says increasing at a decreasing rate, I'm thinking of this sort of picture. Decreasing at an increasing rate, I'm thinking of something that's a function that's doing that. And then similarly, if we have our concave up, on this side, it's decreasing at a decreasing rate, right? It's getting less and less and less steep. So decreasing at a decreasing rate. And then finally, increasing at an increasing rate. So concave up, the two words match, and concave down, they are opposite each other. Okay. So there's a few things about the second derivative. Couple more. So, here's time. Here's our COVID-19. Positive rates, or positive numbers. And pretty much what we saw, actually, some nice data for Kentucky that if left unchecked, probably what most of these diseases would do would be something along the lines, at least in the beginning. They would start out and they would grow faster and faster and faster, so they would be concave up, increasing at an increasing rate. But at some point, and again, it depends on how virulent the disease is and its access to the population and so forth. But typically, if you think about the spread of something within a population, now something could be information. That's the great thing about math, is the many mathematical models, they don't really care whether you're spreading disease or spreading information or, spreading good cheer. Doesn't really matter. You're spreading something through a population. And typically, it would look like this, but then, at some point, it begins to taper off like that, and possibly what this is doing is, well, here's your full population up here, right? So at some point, nobody else can get it. And so you look at a curve like this, and there's this spot in here, and here we are concave up. It's increasing at an increasing rate, but then all of a sudden, here we're concave down. And so there must be a spot with no concavity. And that's this spot right here, and we call that an inflection point. So where a function changes concavity, we call that an inflection point. And what we see is if we actually take the first derivative at each of these points, right, it's getting bigger and bigger and bigger, right, because it's getting steeper, so the slope of the tangent line is bigger. So it's getting bigger and bigger and bigger. Oh, and then it gets smaller and smaller and smaller. Oh, typically, at an inflection point, that signifies a local extrema for your first derivative. Okay, here, the derivative is at a maximum at that inflection point. I can make it at a minimum simply by drawing sort of the opposite type of curve. If I start with a curve that grows quickly at the beginning, I mean, truly it's very fast here, but then slows down and then starts to speed up again. Well, somewhere in there, I have an inflection point. But what you see is if you're looking at the tangent lines, right, the slope reaches, say, a minimum right in there, but then starts increasing again. So that inflection point here again seems to be an indication of a local extrema for the derivative. Okay, so those are the kinds of things we can see from the graphical language that then port over to the algebra and so forth, that we, we can draw stuff like this and kind of know what it is we're looking for. And so along those same lines, if our job is to find, that is still in there, yeah. It's giving me a question mark, but it's not saying it's gone. Did anybody, I'm curious, did anybody have trouble with the Wi-Fi in this building at all this morning, today? No? You didn't? Okay.
Dr. Ratliff did.
He did? Okay. Yeah. Because I was trying to use this little tablet, and I was having trouble, but it appeared my phone wasn't, so I thought maybe it was just the tablet, but it kept going in and out, and just was curious. Okay, so when you're looking at something like that, right, and you see a minimum, one of the things you see is, yeah, it's the lowest point. Oh, that makes it a minimum. Another thing you see is that the derivative is negative here, positive there, and 0 at that spot. Tangent line is nice and flat. But another thing we see is it's concave up. And now you can make something concave down and have a minimum, but if you do that, the derivative's undefined there anyway. Okay, so if you have a nice derivative, so here I couldn't talk about the concavity at that point, because it's undefined there, just because it's the derivative of the derivative. Well, the derivative's not defined there. Okay, so if the derivative is defined and then the second derivative is defined, what we'll be looking for is whether we're concave up or, in the case of a maximum, concave down. And then I don't need the first derivative test necessarily, right? Because, well, if I have a critical number due to the derivative being 0, and I know I'm concave down, must be a maximum. And if I have my critical number where the slope's 0, and I know I'm concave up, must be a minimum. And so that's in 3.4, they talk about the second derivative test, and that's the kind of thing we'll be looking at. Okey-doke, and I think we are out of time. And so we'll call that done, and I will go ahead and open up that link. And then later today, I'll do the upload, but I'm guessing nobody will be done with it like in a couple hours or so. Okay. So, here. Stop. And exam 1. Available. Okay. Make sure it looks good. Yep.